So welcome to this quick tutorial on how to use OpenSees to do 2D truss analysis using or in Python. The main aim of this tutorial really is to act as an entry point into using OpenSees. OpenSees is a fantastically capable library, freely available on the internet. You can download it, install it, and get using it, and it's packed with capability. And so we're only going to scratch the surface in this tutorial, but the main aim here really is for anyone who is completely new to OpenSees. You mightn't even have heard of OpenSees before. It's to help you get into it, and we're going to do that through an example. It's usually the best way to try and learn anything new is to try and do something useful with it. So we're going to use OpenSees today to analyze a simple 2D truss. Nice entry point. So that's going to be the objective. When you get to the end of this tutorial, you can go off on your own and do your own truss analysis, and you'll see that it's a fantastic tool to have at your fingertips. So everything that we write, all the code that we write in the tutorial today is going to be, or it's already in a written tutorial over on engineeringskills.com. So if you head over to engineeringskills.com and navigate to the tutorials page, here we are here. This is a list currently at the time of recording of all of our current tutorials, and the one you're after is this one, an introduction to OpenSees and OpenSeesPy for 2D truss analysis. So if we head on in there, you've got a full write-up of this entire tutorial, basically everything that I'm going to do. And if you register a free account, completely free, just register your account, you can download the Jupyter Notebook and all the code that we write. Right, so that's where to go and find all the materials. I'll give you a super quick, brief background on OpenSees because we want to get into coding as quickly as we can. So OpenSees, it stands for the Open System for Earthquake Engineering Simulation, developed primarily, I believe, by a guy called Frank McKenna in the late 90s. So it's around a very long time. And it was developed at the Pacific Earthquake Engineering Research Center at UC Berkeley, I believe. So you can read up more about the background on it. We're not really that interested in the background for the purposes of this video. A little bit more about it in our tutorial here. But what we really want to do is get straight into coding. So before we actually get into coding, I think it's probably worth addressing the point, why use a library like this? Why should you be interested in OpenSees, right? If presumably you're an engineer or you're some way related to engineering, why use this OpenSees library? And why am I telling you that you should be interested in using OpenSees? Because I primarily, if you've followed me for any length of time, you know that I primarily teach people all about how to use Python in structural, civil and structural engineering. And I also teach the theory behind a lot of the analysis techniques that we see implemented in software. And so I am a really strong advocate of understanding how the software works. And so I believe at least, that if you're using analysis software, you kind of have a responsibility as an engineer to really understand what's happening behind the scenes. And if you go on Engineering Skills, you'll see I have loads of courses teaching all about how the software works. And so here I am now coming along and saying, well, here's a library, essentially a black box, that will do a lot of the analysis for you. And I do, despite thinking that and believing that you should understand the nuts and bolts of how all these things work, there is no harm in making use of a sort of a battle-tested library like OpenSees to do analysis once you've already understood what's going on. You don't always have to write your own code from scratch. If there's some code out there that's been validated and is known to work well, by all means dive in and use it. And so that's our approach here. So that's the idea. So what are we going to do today, right? We're going to analyze a truss. So if I switch over here to my Jupyter Notebook, so I've got a split screen here, right? I am in Jupyter Lab. That's how I tend to prefer writing my Python code in a Jupyter Notebook, and I use Jupyter Lab. You might use VS Code or whatever. You can use whatever you like. So that's what you're looking at here on screen. On the left of the screen is the code that we wrote in our 2D truss analysis course. So again, you'll see it referenced in the written tutorial, but I have a full course on how you write the code from scratch to do 2D truss analysis. And this is one of the examples from that code. Now I'm bringing it up here because this is going to be essentially our ground truth, right? So we're going to implement a code or write a code that uses OpenSees, but we're going to base it on this example. And so when we get to the end of our OpenSees code, we can compare the results and make sure everything agrees. And spoiler alert, it does. But essentially that's why this is here. I also wanted to bring this up because I think it's really helpful for you to see, if you haven't gone through that course yet, for you to see the various different steps that are required in order to reach a solution for a structure like this using the direct stiffness method, right? So here we are, we've got a simple inverted bowstring truss here. We've got a pin on the left at node 1, horizontal roller on the right at node 5, and we've got some loads applied. I will say as well, when you're doing any kind of analysis like this, a well-labeled diagram is like a must as a starting point, especially if you're doing direct stiffness method stuff where you've got numbered degrees of freedom, you've numbered nodes. You really got to have a nice clear diagram. So that's what we have here. The first point in any kind of analysis really is to state what are your constants and define your model. So I'll whiz down through this super quick and then we can get coding the new version. Right, so we've got Young's modulus established here for our material. We're dealing with steel. We have a cross-sectional area defined for all of the members within this truss. And then we have a scale factor here, which is set to 500. That gets applied to our deflections so that when we plot them, we can actually see them. All right, now this will be relevant, the node definition and the member definition. This will be relevant in our new code as well. So our nodes are essentially defined as follows. Each row here, so this is a 2D array in Python essentially, right? So we have that there is node 1, and that's the x coordinate at 0 and the y coordinate at 6, and then with the same thing for node 2, node 3, node 4, etc, etc. That's how I'm storing the positions of my nodes. We come on down and we have then the connectivity matrix, it's sometimes referred to. It's just a 2D array that specifies the node number at the start and end of every member in our structure. So this is member 1 goes between nodes 1 and 2, member 2 goes between nodes 2 and 3, and so forth. So you can store this information whatever way you like. This just seemed to be the most logical way to me to store this this structural information. Moving on down from that, we have our degrees of freedom, our restrained degrees of freedom specified. So that's saying that degrees of freedom 1, 2, and 10 are restrained, and that will, if I look at my diagram here, node 1 has 2 degrees of freedom in the x and the y direction. They are numbered 1 and 2, and so that's my pin restraint at node 1. And the vertical restraint, or the y restraint, at node 5 has degree of freedom number 10. Okay, so that's where those numbers are coming from. Again, by the time you've gotten to this particular lesson in that particular course, this isn't news to you. You'll have gone through all this and you'll understand this. I'm kind of covering it here super quickly to provide the context necessary before we jump over to OpenSees. And then we're just specifying some loading information. Again, we won't dig too much into the detail here other than to say that minus 10,000, minus 30,000 and minus 5,000, those are newtons, not kilonewtons. You can see those are the kilonewton loads applied here, and I'm storing them as newtons. I tend to work in newtons and meters as my my units when I'm doing any kind of analysis. In our full code, we first of all plot the structure to make sure that all of our information has gone in correctly. So that's this plot here. There's the code. We will write the code. I'll go through all this code when we write our OpenSees version, because we're also going to do some plotting with that as well. But really what I want to get to is this. How do you do an analysis? What are the stages involved in a direct stiffness method analysis? So some sort of pre-processing, I guess you could call it here. I won't go through all the code, it's just too much for one video. But the sort of pre-processing involved is calculating the member orientations and lengths. We would then come down and define the stiffness matrix for the structure. So the stiffness method works by analysing every individual member in the structure. And they're all simple members. We come up with a stiffness matrix, a 2x2 stiffness matrix in this case, for the individual members. And the beauty behind the direct stiffness method, the magic in it, is that you can, with knowledge of how that structure is connected together, you can take those individual stiffness matrices and you can combine them into a much larger stiffness matrix for the structure. And that stiffness matrix encodes the connectivity in that structure, and essentially it encodes the stiffness of the structure, right? It's the structure's resistance to externally applied loads is captured within that matrix. We build that. I mean, that's the real nub of it, right? That's where the I suppose all the work is in working out, in writing the code to build that primary stiffness matrix, we call it. But at that point, the stiffness matrix is really just a big matrix, right? but it's kind of floating in space. You can think about it as floating in space because it doesn't yet have any information about the restraints, the external restraints that are locking that structure down, in this case a pin and a roller. And so what we do then is we layer on knowledge of those constraints, and there's a very systematic way that we do that, but we sort of, I'll just say for now, we layer on that knowledge, right? And what that does is it takes our primary stiffness matrix, the one that's floating in space if you like, and it locks it down, okay? And it turns it into what I call a structure stiffness matrix. And it's that stiffness matrix that we will invert. This is why you got to use a computer to do this, right? Because inverting a matrix, if you cast your mind back to your engineering mathematics all those years ago, or maybe quite recently for you, inverting a matrix is a painfully slow and tedious process, especially as you get beyond anything like a 3x3. You need to get into bigger matrices, forget about it, you need a computer to do it. And that's why we always implement this method with a computer. So you invert the matrix, you multiply it by the force vector, the externally applied forces, and you get the displacements. And then with a little bit of post-processing after that, you can work out what are the forces in the members, because if we know the material properties and we know the displacement at each end of the member, we can work out what force caused that displacement. And then you can, again, a little bit of plotting thereafter. We can look at the force distribution, we can look at the deflected shape of the structure, and we can plot out all of the information that our analysis has yielded, right? So that is, if you're writing a code from scratch and you want to know how to do that, go to the relevant course that I have. But that's essentially what you do, right? That's all of the different steps. Now, when we write the OpenSees version of this code, it's way shorter, right? Because a lot of the hard work has been already done, right? It's behind the scenes. Pretty much the same stuff is happening. We're just going to call a method that will do it for us. Okay, so enough sort of said. Let's crack on here and write some code. All right then, so let's start off by importing OpenSees. This presumes, by the way, that you've installed OpenSees, and you can do that in the terminal if you're on a Mac by just doing pip install OpenSees. And in fact, if I jump over to our tutorial, our written tutorial, let me see, somewhere down here. So pip install OpenSeesPy. So presumably you've installed that. Once you've installed it, you can import it into your notebook. All right, so I'm importing OpenSeesPy. I'm importing everything. I'm going to import math. I don't even know if I'm using that, but I import that at the top of pretty much every notebook anyway, because I use it quite often. I'm bringing in NumPy, and we'll do a bit of plotting. So I'm bringing in matplotlib. So we'll execute that. We've got a diagram here, so we won't bother bringing another diagram in. But what we'll then do is we will take our constants, our nodal definition, and our member definitions. So let's take those guys and drop them over here. Okay, so we've got all of our information essentially that we need for now. So now we can plot the structure. Now, if you've taken that course, you've taken more than one of my courses, you've seen me explain this plotting code a lot of different times. So what I'll do here is, rather than typing it out line by line, I'm going to copy it over, and I'll briefly then just explain it. So let's just collapse that down. So what we've got here is we are defining a new figure, we're adding a set of axes, we're setting the scale of the x and the y axis as being equal, because we want this thing to be an accurate representation of it on the 2D plane. Then we're just cycling through in a for loop each of our members. That members there refers to the member definitions 2D array up here. So we're cycling through. So I've documented this code reasonably well. So we've got we're extracting the node number for node I, the node number for node J. That's encoded in the member definition itself. With the node numbers, we can then reach into the nodes array, okay, which was this guy here. So we can reach in there for the given member. Remember, this is happening inside of a for loop. And we can extract the x and y coordinate for node I and the x and y coordinate for node J. So that's what's happening here. I have here the index. I'm calculating the index of the association degrees of freedom. If I recall, I don't think I actually need to do that. So what we're going to then do is just plot a blue line, essentially with coordinates ix and jx for one end, or for the x values of that line, and iy and jy for the y values at each end of that line. And then we're just plotting a blue circle around the nodes we're adding an X and Y label and a title, turning on the grid and calling plt.show just to get rid of a bit of text that would otherwise be printed out. So we can execute that, and there we have it, right? So the reason I do this is because very often when you're doing an analysis of a new structure, you'll screw something up here, right? You'll make some kind of a mistake up here, and if you don't plot the structure to see, you won't know, and then you'll get all the way down to the end and you'll have made a mistake somewhere up here, and everything else that follows will be rubbish. And so it's a good idea to plot this nice and early. So we've plotted our structure. So what is the next step? Well, now we can get straight into the OpenSees side of things, right? Let's give ourselves a little heading here. I'm going to hit a series of commands here. Now I will urge you to, as a starting point, head over to this tutorial, okay, because I explain the commands in more detail here, and also the documentation, right? So the documentation for OpenSeesPy and OpenSees. OpenSees is the base library, and that is you interact with that base library using a language called TCL. OpenSeesPy is the Python version. If I haven't mentioned that already, I should have. OpenSeesPy is the Python implementation of OpenSees. Now, it's actually really helpful to refer to both sets of documentation, the original, if you like, and the Python version, because although the Python version is pretty much based on the original set of documentation, I think there's more detail in the original set, and so it is really helpful to refer to my article, but also the base sets of documentation. I can't emphasize that enough. Okay, back over here. What we need to do is we start off by removing any previous model that is in memory, and we do that with a method called wipe here, because if you run your code already, you'll have a model in memory, and so when you run it the next time, you'll want to start off by wiping the previous model. So that's what this is all about. Then we come down and we establish what the model, essentially the model builder, right? And we do that with a command called model. We're going to pass in basic, the type of model, and then it's just a keyword that this method requires. And then we're going to pass in a flag, and the flag is going to be the dimensions, so the number of dimensions. Again, you'll get all of this from the docs. If you're wondering where I got it from, I've just read the documentation. And then we're going to pass in another flag to indicate the number of degrees of freedom per node. We're dealing with a 2D truss, and so it's going to be 2 degrees of freedom per node. The next tutorial, which is coming out, it's produced, I just have to release it, we're going to do some frame analysis, some portal frame analysis, and in that case we would have 3 degrees of freedom per node. Again, it's a 2D structure, and so we can stick in here the number of degrees of freedom is going to be 2 as a number, not a string. All right then. So let's just make sure that works. That works, excellent. And we'll add in a couple of comments here to keep things tidy as we go. All right, next we can come on down and we can do our node definition. To define our nodes, we're going to use a command called node, okay? And what this command does is it takes a tag number, right? So you give each node a number, essentially. It's referred to as a node tag, and we will then specify the X and Y coordinate of that node. So that's pretty straightforward. Now, we'll write a for loop so that we can, in one hit, just cycle through all the nodes and call this command for each one. So that's the strategy here, right? So I'll say for loop in Python, right? So for I and n, okay. So I will just be an iterator that increases by 1 every time we move through, and then I'll say enumerate nodes, right? So remember this nodes here is referring to this 2D array up here, right? So we're cycling through each one of the nodes defined up there, and then every time we run through, probably don't need to explain a Python for loop to you, but anyway, every time we run through this for loop, n, this n here will take on the value of one of the nodes in our nodes array, right? So I'm going to call, now here's a gotcha, right? So node, N-O-D-E here that I've just written, that's a method in OpenSeesPy. So don't be tempted to, as I did originally, don't be tempted to use that as a variable name, because you'll just confuse things in your code and it won't work as expected. So I'm calling a method here, node, from OpenSeesPy. I'm going to give it a tag number. Now a sensible tag number will just be I plus 1, right? Because for a Python for loop, I, the iterator, starts at 0. I don't want the node tags to start at 0. I want them to start at 1 and increment by 1 for every node, right? So that's where the I+1's coming in. And then we will specify the coordinate, the X and Y coordinate. So the X coordinate is going to be stored in N at position 0. And the Y coordinate is going to be stored in N at position 1. Now, another gotcha with OpenSees is it's pretty particular about the data types that it expects to receive in methods. And so you'll see what I had to do here was specify or explicitly cast that as a float. Okay, for that to work. And I think it would be helpful to also have a little print statement here, and I'll say print an F string to just say let me see, node I+1 defined. So we'll say node, and then we'll put in a variable I+1 and we'll say defined. So if I run that now, we'll cycle through all the nodes and we will define every node in our model. Of course it didn't work. What am I doing? I'm doing something stupid here. What is it? Okay, this is the problem. That should be a square bracket, not a curly bracket. All right, let's try that again. Okay, still have a problem. What is it? Okay, so I made the mistake that I was literally just cautioning you against. I used the word node here because remember I copied this code straight across from our previous code, and you'll see that I've used node here, right? So node has taken on one of the values in the nodes array in this previous for loop that we used in the plotting, and so that's the issue. So let's just change that to an N. Hopefully that works. Okay, so now I can come down. In fact, I should probably start from scratch because node is saved in memory as something else. So let's see. Now that hasn't worked because I need to change that in my plotting code to an N and that to an N. Let's try that one more time. Okay, that's worked. So remember, OpenSees expects node to be one of its inbuilt methods, and so I shouldn't be renaming it as something else. Right, let's call that. Brilliant. Okay, so now we have defined all of our nodes. Let's rapidly move on here to define all of the members now that we have our nodes. Right, so the first thing we got to do here is define a material. Now, OpenSees has a lot of different materials that we could use. In this case, we're going to use a simple material, a uniaxial material it's called. So we will call uniaxial to define that material. We'll call a method uniaxial material. We're going to pass into that the option elastic with a capital E. Elastic. We will give it a material tag of 1. That's just how we can refer to that or reference that material elsewhere. And we'll pass in Young's modulus. Now we've saved Young's modulus as a variable E, so we'll just stick it in there. So that defines a material. And now let's do the similar idea. Let's cycle through all of our members and define each one. So we'll say another for loop. We'll have an iterator I that goes up by 1. So we'll say I and member in enumerate members. All right then. So that's grand. Now that we've done that, we are going to call another OpenSees command element. This is what we're going to use to define each element. We will pass in an element type, which is Truss. We will give it an element tag. Again, every time you define something, it gets a tag so you can refer back to it. Right, so that's an element tag. It can be I+1 again, for the same logic we used previously. We then want the node number at node I and the node number at node J. Right, so is that correct? We want... Yes, the node number at node I, the node number at node J, right? So we will, and they need to be integers, so I'll explicitly cast them as integers, right? So I'll say, as an integer, let's extract the node number for this member at node I, which is going to be 0. So that member there is referring to that member there. And we will then say, again, as explicitly as an integer, we will have MB or at position 1. So that's the node number at the other end of that member. All right then. So we'll give it a cross-sectional area. And then we've got to specify a material ID. Now we already defined a uniaxial material with an ID of 1. And so the material ID that goes into that argument's location is 1. Let's add a string to just say each member has been defined. And let's try that. And we've made a mistake. An easy one this time. We just spelled something wrong. Enumerate. All right, still got an issue. The issue is because I've tried, this is another one of these gotchas, right? I think this is the issue. I've run this cell, right? And so I executed that line, and then I came into the for loop, and I tried to run the for loop, and I hit an error at this point. But this previous line executed correctly, and so there's a material with tag 1 stored in memory, and so when I've tried to execute it again, it's come back to me and said, hey, hang on a second, you've already got a material with tag 1, and so that's where this wipe command comes in. So you'll find you do this quite a lot. You end up starting up here and wiping everything, and then going down and executing again. That was indeed the problem. So now we have each of our elements defined. Okay, we're in good shape. We can move on now and define the boundary conditions, and that is mercifully straightforward. All right, we're going to use the fix command, again, straight from OpenSees. We will specify a node number. Node number 1 is going to be fixed in the X and Y direction, right? So that's going to be, fixity is indicated by 1 and freedom is indicated by 0. So that's going to be fixed in the X, fixed in the Y, and we'll fix node 5 not in the X direction, but in the Y direction. Okay, so that's a roller, horizontal roller at node 5. Run that, great. Let's define some loads. So defining loads is a sort of a multi-step process for us. So now we are going to start defining loads. We're going to start off by defining a time series. So that's the load definition process always starts off, first of all, by defining a time series. The number of steps that is required to do various different things, in this case define loads, is a hint at the degree of customization that you can generate using OpenSees. We're doing a very simple static 2D analysis of a truss. It's about as simple as it gets, right? But OpenSees is capable of an awful lot more, and you'll see that as we start to call these commands and pass in options to them, again, that's a hint at the degree of customization and complexity you can achieve with these commands, right? So I'm generating a time series. I'm going to pass in constant, and I'll give it a tag of 1. So that's the time series tag. I then got to create a load pattern. You'll be used to this idea. All loads, it must exist within a pattern. And so we're going to define a pattern. It's going to be plain, and it's going to be now. Well, I know it's 1 and 1. So that's your pattern tag is the first one, and the second one is your time series tag. Now, the actual specifying of the loads again is very straightforward, right? So if we look at our diagram here, right, we want a load in the negative Y direction at node 2, and so that is specified by saying node 2 0.0, it expects a float, okay, so 0.0 in the X, and a negative, so it's the global reference frame that we're in, negative 10,000 in the Y, again expects a float, so give it a float. So that's how we define the first 10,000. We'll just copy those down and change what we need to. So then we're adding to node 3, that's going to be minus 30,000. And then we're adding to node 4, which is going to be minus 5,000. All right, and that is our loads defined. Simple as that. Okay, so now we can set about doing the analysis. And again, you'll see that we've got to do, I think it's 7 commands here. Now, the 7 commands feels like a lot. I mean, it doesn't feel like a lot when you've written a code as long as the code on the left there, but it feels like a lot for, you know, just telling it to just do the analysis, right? But again, this is sort of saying to you that there's a lot of possibilities that are open to you depending on the analysis that you're doing, and so just sort of keep that in mind. Okay, so let's just do our analysis. First thing we do is define a system of equations. Okay, and the way I think about this is essentially like an object that is going to hold our system of equations. That's how I think of it, or have interpreted the documentation. Right, so we're going to specify a type of system of equations, and it's band SPD. Now that is referring to, that's a text cell, that's why that's not looking like code. Right, band SPD. I'm going to write some notes here as I go, or at least a heading. So we're creating, or we'll just say create SOE, system of equations, using this particular option. In the next tutorial where we do some 2D frame analysis, you'll see that we use a different system. We're not going to get into it. You can read the documentation that I reference, but that system with that option, band SPD, is suitable for the truss analysis that we're doing right now. We then are going to create what's called a numberer. or we'll call numberer to essentially specify how our degrees of freedom will be numbered. And we've got to pass in an option, because there are different ways, believe it or not, for how that will be handled. And so we'll just say numberer, and we'll pass in RCM. Now, again, there's more detail in the written tutorial on this. I'm going to refer back to see what does RCM even stand for. So RCM is the reverse Cutmill-McKee numberer. There you go. So again, refer here for a little bit more detail. I just can't keep all this stuff in my head, to be honest with you. So we are creating a degree of freedom numberer. Okay, that's fine. Now we want to call constraints and specify plane, and this is again controlling how constraints will be applied to our system of equations. So create a constraint handler. Right, so we will say constraints plane. All right, and now we are going to create an integrator. So we'll call the integrator command. We're going to pass in load control, and we're going to specify 1. And this essentially is saying that we will be, it's how we're applying our load is going to be based on load control rather than, for example, let's say displacement control. If you've done experimental work, you'll have come across those concepts of applying load and controlling the load application based on the load that gets applied versus controlling based on the displacement that gets produced as a result of the load. So we're going to load control essentially is what's suitable for us in this analysis, and we're saying that our load is going to be applied in one simple increment, because again, this is just a straightforward static analysis, and so a single application of our load in one increment will be sufficient. Then we are going to specify the algorithm, and we will use a simple linear algorithm. What type of analysis are we doing? We're doing a static analysis, and so we'll specify that. All right, so that's 1, 2, 3, 4, 5, 6 commands are specified. So again, what are we doing here? At each of these different steps, we are specifying one of the things that it's important, that essentially finely tunes our solution process. So we specified all these things, and now we can just tell it to analyze our structure, in a single analysis step. And so we are going to just do one analysis step, and that's what that one refers to there, rather than performing the analysis in a series of, or breaking it up into a series of steps, which would, you know, I'm sort of thinking as I'm talking here, which would probably be much more important for a structure that's going to experience a geometric nonlinearity. You're going to want to break that analysis procedure. Be a nonlinear analysis, but you'll break it up into a number of steps. This is a simple linear static analysis, and so a single analysis step will be fine. Now, does that work? It works. The little 1 that, or the little 0 here that came out at the end tells us that it's done. The analysis worked fine. Okay, so now we're ready to analyze our results and compare them against our previous code, or our other full stiffness method code. So let's start off here with a heading, give ourselves a bit of space here. So the first thing I want to do is I want to print out the displacement, the X and Y displacement at each node, because over on our original code, we have that, right? We've got that here. So I want to print out the results that we got from OpenSees and just make sure that my code agrees with OpenSees. All right then, so this is pretty straightforward. We are going to, let's see, well, because I'm a little bit pedantic, I like to make sure my printouts are a little bit clean. So I'll say I'm going to print a little heading here called node displacement. All right. And what I want to do is cycle through each one of my nodes and use a method from OpenSees to extract the X and Y displacement that it has calculated for me for each of the nodes. So again, we'll cycle through each node. Now, the command that we use to extract the X and Y displacement is called node disp. That's an OpenSees command. We will pass in the node tag. Now the node tag is going to be I plus 1 for this particular loop iteration, and I would like first of all the X displacement. That's going to be achieved or obtained by passing in the argument 1. So that would be the X displacement. And so what I could do is I could define, or I could rather assign the output of that method to a variable called UX. Let's do something similar for, you can see where I'm going with this, for the Y. So the Y is going to be the exact same, except I'm going to reach in and extract the second displacement using node disp. Now that's going to give me a number with a whole load of decimal places, which I don't want. So let's round it to 5. Remember, it's going to be in meters. And so it's going to be a 0.00 something with lots of decimal places. So let's round whatever we get back to 5. And then let's do a print statement. So not a print statement, yeah, a print. We will print a string and we will feed into that string variables ux and uy. And with a little bit of luck, I'd never be that lucky, enumerate. Have I misspelled that again? I have. Enumerate. Okay, here we go. So let's see. These are the displacements that OpenSees has given us, and over on the left, these are the displacements that we obtained previously. And sure enough, thankfully, they agree, right? So we have been able to obtain, we've solved our problem, and OpenSees has worked for us. At this point, we know it's worked, everything's hunky-dory, and because these displacements agree with these, now it's just a process of extracting more information from our analysis. And, if I was to expand all of the cells in this code on the left, it's really long, right? There's a lot there. If you compare that to what we had to do here in OpenSees, right? It was pretty straightforward. And actually in the next tutorial on this, where we do some frame analysis, you'll see that I don't even have to do the plotting myself. I can use another library to do the plotting, which we'll get to. Which you got to define your structure. As far as OpenSees is concerned, we just got to do a handful of commands, right? We've got to establish our model, define our nodes, define our material, define our elements, define our supports, define our applied loads, all very straightforward stuff. This is sort of out of the box commands that you're going to, let's be honest, just copy and paste 90% of the time. And then boom, you're done. So it's very quick. That's why I'm such an advocate of using these kinds of libraries and getting familiar with them, because it's so fast, right? You can just blast through an analysis in no time. Again, I always say it's good to understand what's doing behind the scenes, at least at a kind of a fundamental level. So let's move on here, and will we plot the displacement? Let's plot the displacement. The plotting is going to be, in fact, there's a fair bit of code there, but we've seen the vast majority of it before. So what I'm going to do is just drop it in, right? So again, we go through this code in detail over in the course, but in a nutshell, define a figure, add some axes, set the scale to the x and y axis equal. We establish a scale factor. I think I previously established that at the top of the code, and we cycle through each member. We extract the node number at node I and node J of each member. We use those node numbers to reach into the nodes array and extract the x and y coordinate at each end of the member. That's what's happening here. We've done this already previously. And then we plot the structure this time, and we saw that already. I'm just plotting it in gray. Then what we're doing is we're reaching into node disp, or we're using that method node disp from OpenSees to extract the x and y coordinate, or the horizontal and vertical, I shouldn't say coordinate, it's the horizontal and vertical displacement of the relevant nodes. And then we are just essentially constructing a new line for each member, where the line is not the line in its original position, it's the line with the original positions but shifted in the x and y direction based on the displacements. So that's all that's happening in that, and we're multiplying those displacements by the factor as well so that we can see it. And then we're just doing some housekeeping to tidy things up. So if we execute that, we get this lovely diagram here, which is essentially the grey lines are our original position, our original structure unloaded, and then the red lines are the displaced structure. And that's just is something personally I think immensely satisfying about writing the code that takes you from the very start, the structure definition, down to something like this. I just find that every time particularly satisfying. So that's it. That's the displacement. Before we wrap up, let's just extract the axial forces, because you'll see we have those calculated here. Now, if the displacements were correct, we know the axial forces will be correct, but it's still going to be helpful for you to see how do we extract those. So let's just do, this is our last code block here. Let's just do another print member member forces, lovely stuff. I'm going to define a bucket, essentially I refer to them as, right? It's just a container, a data structure, member forces, and it's just going to be a bucket that I'm going to place all of these member forces into. Let me see, so it's an empty array. Then I'm going to come along with a for loop, and I'm going to iterate true for I is the iterator, member is the value each time, in a new, spell it right this time, enumerate members. Okay, so cycling through each member, what am I going to do? I'm going to use the command basic force from OpenSees. I'm going to pass in, okay, I'm going to pass in I plus 1. That's the member tag, right? So that's the member that I want the force for. Now, let me see. That's just going to give me a force. I want to extract. It'll give me a force within an array, I'm pretty sure, if I remember correctly. I'm going to extract the number out, so that's what this, that's me in extracting the number out of that array. It's going to give me a force in newtons, because that's the units I've been using up until now. It's the units I specified the externally applied load in. I want to read kilonewtons, so I'm going to divide that by 1,000, and then I'm going to do my usual trick of rounding that off, because I don't want to see a whole heap of numbers. I'm going to round it to 2 decimal places, and then I'm just going to store that. Well, I'm going to assign it to something first, so I'll say axial force is equal to that, the axial force for this particular member, and then I'm just going to store it, right? So I'm going to say, I don't even need to do this storage bit, I don't think, but I did it in my original code, and I've probably just copied it across. So member forces, I'm going to append into that empty array. So I'll do np append. I'm appending into member forces. What am I appending? I'm appending in the axial force. Okay, that's good. I didn't actually need to do that. But I'm going to now print a print statement. This is what I really need, because this is what I'm going to use to compare with what we have on the left. So I'll say so it's an F string. That's the term I was looking for previously. Force in member. It's going to be member I plus 1. Okay, that's cool. What are we going to say? Let's be really clear about this and say that it's going to be nodes MB or 0. So I'm just specifying which nodes. So the same way I have over here on the left, I'm saying nodes 1 to 2 for member 1. I'm creating the same string over here. So I'll say member 0, 2, and then we'll pass in member 1. Pretty sure that's going to do it. Let me see. Let's say is, and then we'll pass in axial force. And let's not forget our newtons. I used to tell students off all the time for forgetting to specify units, so I shouldn't do it here, or shouldn't forget. So let's see, will that work? It did. Amazing. All right, so there we have it. So there is the axial force for each of our members, and sure enough, as we would expect at this point, it's in perfect agreement with our code on the left, where we did the sort of complete analysis step by step ourselves, rather than relying on OpenSees. So I mean that's it. That's the you could go ahead and do. I won't do it now because it's pretty trivial, but you could go ahead and plot this diagram now next, which is the very same as plotting the original structure, except when we come to specify the color of the element, instead of just specifying it as gray or red or whatever, if the force in that member is negative, make it red. That's what I've done there. Or if the force is positive, make it blue. So I won't bother doing that now. You kind of get the idea on how to do that. So there you have it. I hope you found using OpenSees, or you're seeing me use it and you've kind of realized, wow, there's actually, it's pretty straightforward. There's not a lot to that, but I can get a lot out of it, right? So it's a great library. I highly recommend it. Once again, I'll say jump over to engineeringskills.com and the full written tutorial. Anything that I have sort of skimmed in terms of my explanation as I'm moving through and writing the code is elaborated on a little bit more in this tutorial. So head head over there and get yourself the code as well. Register your free account and you will be able to download that code. So that's it for this tutorial. I've already written a really nice tutorial actually that I've written the code for it, and so that'll be published shortly, where we do some 2D frame analysis. And so again, you can kind of think of that as the next step up, where we're going to be generating bending moment diagrams, shear force diagrams, and in that tutorial actually we use a visualization library, so we don't even have to write the code to do the shear force and bending moment diagram. We'll use a library for that as well. So keep an eye out for that one. That's coming pretty soon. I hope you found this helpful. I hope you're kind of inspired and interested to go and see what else you can use OpenSees for. I can see a long series of tutorial articles stretching out in front of me on OpenSees. I'm pretty excited to explore what this library has to offer and to share that with you as I go. All right, that's it for this one. I will see you in the next one.